Hi, I'm Greg Norton. I'm here to talk to you today about ViaSat's latest enhancement to the ViaG1000. The ViaG1000 is a Mark 12A IFF test set that has some of the most robust capabilities on the market today. The ViaG interacts with both commercial and military Mark 12A interrogators and transponders to generate a realistic, dense, coherent Mark 12A IFF RF environment. The ViaG allows the user to create up to 50 independent platforms, air, sea, land, ground, and fixed, and the user can create up to 50 independent Mark 12A interrogators or 25 independent replies. The ViaG is capable of generating all Mark 12A modes. For the encrypted modes, the ViaG interacts with a real crypto device, either a KIV77 or a Celex SIT 2010. All the RF that is generated by the ViaG is coherent for each of the platforms and emitters in this scenario. The ViaG generates a realistic, dense RF environment for testing interrogators and transponders. For our previous video, we demonstrated the ViaG interacting with a Mark 12A transponder. For today's video, we'll be demonstrating the ViaG interacting with a Mark 12A interrogator and generating up to 25 independent replies. The setup of the ViaG1000 is very simple and consists of only 3 connections. The first connection is an Ethernet connection to a laptop or desktop computer. This Ethernet connection provides a user interface to the ViaG. There's no software contained on the laptop. All the software is contained on the ViaG1000. The ViaG1000 contains a web server that allows the laptop to connect to a simple web browser to provide a graphical user interface. This interface is going to be displayed on the monitor to your left. The second connection is going to be to our system under test. Our system under test is a Mark 12A interrogator. We're going to be taking the output, the RF output of the Mark 12A interrogator, connecting that to the RF input of the ViaG1000. And then the ViaG RF output is connected to the Mark 12A interrogator's RF input. If your system has a single input-output connection, then we put a circulator onto the front of our system to separate the RF into input and output. The interface to the ViaG1000 is through a web browser. Today we'll be using Mozilla Firefox. The ViaG presents a graphical map of the world and a single airplane icon which would represent the system under test. All the RF that we generate will be relative to the system under test. I'm going to zoom in on the map a little bit, get a little closer. To add platforms and emitters to the system, it's a simple point and click. Right click, platform, add, provides an airplane. And then right click, edit emitters. We'll add a Mark 12 transponder, hit apply, and we now have a transponder replying to the interrogations from our system under test. Now, it's a little unrealistic in that we have an omni antenna on the system under test, but for demonstration purposes, this allows me to put the platforms anywhere in the scenario and you'll see the responses. Later in the demonstration, I will make it a main lobe antenna and a directional antenna so we show a more realistic representation of the RF. We've tapped into the RF input and the RF output of the ViaG1000 and fed that into an oscilloscope so we can see the interactions between the system under test and the ViaG1000. That's displayed on the screen on your right. You can see at the top we have a 10 millisecond continuous display which is showing in green the interrogations we're receiving from the system under test and the associated replies that were being generated by the ViaG1000. There are 4 interrogations every 10 milliseconds. Down below we have a magnified view which is shown within the gray box on the top, which gives a little closer view of the pulses being generated for both the interrogations and the replies being generated by the ViaG1000. ViaG1000 is a real-time environment generator, so as I take the platform and move it closer to the system under test, you'll see the response in time move closer to the interrogation, and you also see the power level increase. Let me show you some of the parameters that we can modify for each emitter. Each emitter is completely independent. We have parameters for all the modes, for SIF mode, mode 4, mode S, and mode 5. For the SIF mode, we can modify the emergency mode or identification position. We can turn X pulse on. We can enter in transpond codes for 1, 2, or 3A. We're receiving a mode 3A interrogation right now, so I will enter in a 3A transpond code. We can also adjust the pulse characteristics of the reply, the pulse width, reply time, the fall time, the pulse spacings. I'm going to hit apply, and we're now going to put that transpond code into the data in our response. So now we're responding with a 7700 reply code. The ViaSat is capable of responding to all Mark 12A modes. Right now we're responding to a mode 3A. If we change the interrogator to interrogate with a mode C, you can see the interrogation changed, and we respond with now the altitude of that platform. I'm going to go ahead and take control of this platform. Each platform is also independent, has 6 stop motion models. We can adjust the velocity, acceleration, altitude, climb rate, pitch, roll, heading, and turn rate. I'm going to give this platform some motion. I'm also going to increase its altitude to 20,000 feet and give it a climb rate of 25 feet per second. This system is completely coherent, so you can see as the platform moves in time, the response moves closer in time to the interrogation. You can also see the data within the reply is coherent, and that as the altitude increases, the data representing the altitude also changes. I'm going to take this platform and give it a racetrack flight pattern, so it'll fly in circles so it doesn't fly off the screen. And I'm going to generate a second platform under test and also give it a Mark 12A transponder. Okay, we now have 2 airplanes responding to the single interrogation, a moving platform and a stationary platform. And you can see the platform that is moving is making a turn, so soon those pulses will start moving away from the interrogation. I'm going to make one adjustment to the stationary platform, in that I am going to disable its Mode S capability, so it will not respond to Mode S. Now, as we make adjustments to the interrogation, you'll see each platform will respond independently. So as we change to a Mode A only all call, the Mode S capable platform will not respond, and the platform that is not Mode S capable, the stationary platform, will respond with Mode A. So there you can see it. As we change to a Mode S AS all call message, in which case the Mode S platform, the moving platform, will respond with Mode S, and the stationary platform will respond with Mode A. And they're right over the top of each other, a good chance to show garbling, but let me actually move this platform away so that they're not interfering. And you can see the Mode A response there is stationary, and the moving platform is responding with Mode S. As we switch to the Mode C only all call, the moving platform will not respond, and the stationary platform will respond with altitude. And then as we change to the CS all call, the Mode S platform will respond with Mode S, and the non-Mode S platform will respond with Mode C. I'm going to take this platform and now make them Mode S capable. Now both platforms are responding. Currently, the Mark 12 interrogator is responding with a UF11 broadcast all call, so both platforms are responding. We can also accept addressed interrogations. The moving platform is address 0, so if we change the interrogation to a UF with address 0, only the moving platform should respond. And if we change to address 1, only the stationary platform should respond. There you go. And then we'll send it back to a broadcast UF11 all call. This allows the user to generate a very dense environment, and it's a very simple user interface, adding platforms and emitters with simple button clicks. Once you've created a complicated scenario, you can save that scenario away and recall it later. I'm going to bring up a saved scenario that is a little denser. In this scenario, we're still transmitting with an omni antenna, so all platforms will respond no matter what the pointing angle of the system under test. We have 4 commercial planes. They're capable of all modes. We have 3 military planes that are not Mode S capable, and we have a ground site that is also capable of all modes. You can see as we're generating interrogations, we've got a garbled effect as platforms are over the top of each other. We can generate to all modes, so if we switch to Mode C, there's the military platforms that were not transmitting before because they're not Mode S capable, now responding in Mode C, and each platform independently is responding with its own altitude. I'll change it back to Mode S, and we'll do some of the other interactive capabilities of Mode S. With Mode S, we can receive in the interrogation the probability of reply, which will tell each independent transponder to reply at a certain probability. Right now we're responding at 100%, so you can see with each interrogation, all the platforms are responding to each interrogation. If we change the probability to reply to 50%, then you should see each platform only reply randomly half the time. There you go. So you see on average, each one's only replying half the time. This is information that's fed from the interrogation, and we're interpreting that on the fly and having each transponder reply independently. If we switch to a 1/16th reply probability, we should see even less density of signals. And then we'll go ahead and switch back to 100% probability. And now they're all responding and all garbled over the top of each other again. If I want to make this scenario more realistic, I could take the system under test. I will display its pointing angle. This stick represents where the system under test is pointing. I take control of the emitter, and I change him from an omni to a main lobe antenna, and I reduce his antenna rate to 10 degrees per second. We now have a more realistic scenario in that only platforms that are being pointed at by the antenna should be responding. So we have the commercial plane off in the distance responding. We're now into a dead area. As the planes come into view, they will start to respond to a little denser environment as you get more platforms involved. These are Mode S interrogations, so only the Mode S platforms are responding, so the military planes are not responding. If we switch to Mode C, now we're in a dead area, but each of the platforms will independently be responding with their own altitude. There's the commercial plane off in the distance. And soon here comes the commercial and the two military planes coming into beam, reporting their altitude. These are just a few of the capabilities of the VRG-1000. You see, the VRG-1000 interacts with real Mark 12A interrogators and transponders to create a realistic, dense, coherent RF environment. Because we're a real-time system, the VRG can also provide additional capabilities like external control of all platforms through a DIS interface, or receiving set pointing angles externally in case you have a scanning radar. Some of the uses of the VRG would be just simple interrogation and transpond testing, dense interrogation and transpond testing where you have more than one radio being generated. We can do controlled flight testing to simulate a flight test prior to the test or to determine anomalies that are discovered after the flight test. We can do interference analysis where we can set up an environment and see if your environment will interfere with the civil aviation radios. We can also do AIM certification testing and much more. The VRG-1000 provides a realistic flight test in your laboratory.